Module 6. Unit 12. Moisture, Clouds, and Precipitation. Water is one of the most dynamic and essential components of Earth's atmosphere, driving many of the processes that define weather and climate. It exists in all three states, solid, liquid, and gas, and transitions between these states through phase changes that either store or release energy. These transitions, such as vaporization, where liquid water turns into gas, and condensation, where water vapor becomes liquid, are central to the atmospheric water cycle. These phase changes involve latent heat, a critical energy reservoir that influences atmospheric processes without directly changing the temperature. Humidity, the amount of water vapor in the air, is a key indicator of atmospheric moisture. It can be expressed in multiple ways, including absolute humidity, relative humidity, vapor pressure, and dew point temperature. Relative humidity, for instance, is the ratio of the current amount of water vapor in the air to the maximum amount it can hold at a given temperature, expressed as a percentage. For example, if the air contains 14 grams of water vapor but has a capacity of 20 grams at 25 degrees Celsius, the relative humidity is 70%. Instruments such as psychrometers are used to measure relative humidity, comparing temperatures from two thermometers, one dry and one with a wet bulb. When the two temperatures read nearly the same, it indicates that the air has high relative humidity. The relationship between temperature and humidity is pivotal in understanding atmospheric dynamics. As air warms, its capacity to hold water vapor increases, and as it cools, this capacity decreases. When air reaches saturation, the point at which it can hold no more water vapor, excess moisture condenses into liquid water or ice. This condensation often occurs aloft in the atmosphere, leading to cloud formation. The cooling of air and the subsequent condensation are closely tied to the adiabatic process, which occurs when air rises and expands without exchanging heat with its surroundings. As air ascends, the reduction in pressure causes it to cool. This cooling continues at different rates depending on the moisture content of the air. Dry air cools at the dry adiabatic rate, approximately 10 degrees Celsius per kilometer, while moist air cools at a slower rate because condensation releases latent heat, partially offsetting the cooling. Air can be lifted by several mechanisms, including convection, frontal lifting, and orographic lifting. Orographic lifting occurs when air is forced to ascend over a mountain range, cooling adiabatically as it rises. This process is responsible for the formation of upslope fog, a type of fog created by adiabatic cooling as moist air is pushed uphill. Fog, like clouds, is composed of tiny water droplets or ice crystals, but it forms near the surface rather than aloft. The stability of the atmosphere determines whether air will continue to rise after being lifted. Stable air resists vertical motion, while unstable air tends to rise freely. The stability of air masses is influenced by factors such as temperature gradients and moisture content. When air is unstable, it rises and cools, often forming clouds and leading to precipitation. Clouds, a defining feature of the atmosphere, are classified based on their appearance, altitude, and formation processes. The three main cloud types are cirrus, cumulus, and stratus, each with its own characteristics and implications for weather. Cirrus clouds are high altitude and wispy, indicating fair weather or approaching storms. Cumulus clouds are puffy and can develop into towering cumulonimbus clouds associated with thunderstorms. Stratus clouds, which form in uniform layers, often bring overcast skies and steady precipitation. Fog, closely related to clouds, forms when air near the surface cools to its dew point, causing water vapor to condense. Different types of fog arise from specific conditions. Radiation fog forms on clear nights when the ground cools rapidly, chilling the air above it. Advection fog develops when warm, moist air moves over a cooler surface. Upslope fog, as mentioned earlier, results from air being forced upward along a slope and cooling adiabatically. Precipitation forms when cloud droplets or ice crystals grow large enough to overcome the resistance of air and fall to the ground. This process begins with condensation nuclei, tiny particles such as dust or salt, around which water vapor condenses. Droplets or ice crystals grow through processes like collision and coalescence, where smaller droplets combine to form larger ones, or the Bergeron process, which involves the growth of ice crystals at the expense of supercooled water droplets. The type of precipitation that reaches the ground depends on atmospheric conditions. Rain, the most common form, occurs when temperatures throughout the cloud and near the surface remain above freezing. Snow forms when temperatures are below freezing throughout the cloud and down to the surface. Sleet and freezing rain occur in mixed temperature conditions, where snowflakes partially melt on their way down and refreeze before or upon reaching the ground. The behavior of water in the atmosphere demonstrates its unique properties and critical role in regulating Earth's energy balance. The latent heat released during condensation and freezing warms the surrounding air, fueling processes such as convection and storm development. Conversely, the absorption of heat during vaporization and melting cools the environment, moderating temperature extremes. The global distribution of moisture, clouds, and precipitation highlights the interconnectedness of atmospheric processes. Tropical regions, with their high temperatures and abundant water vapor, experience frequent cloud formation and heavy rainfall. In contrast, polar regions, with their cold, dry air, have limited cloud cover and sparse precipitation. Mid-latitude regions, influenced by a mix of tropical and polar air masses, experience diverse weather patterns and precipitation types. Understanding these processes is essential for predicting weather and managing water resources. Advances in meteorology, such as satellite observations and computer modeling, have improved our ability to forecast precipitation and its impacts. These tools help mitigate the risks associated with extreme weather events, such as floods and droughts, which are often driven by the movement and transformation of atmospheric moisture. Unit 13. Air pressure and wind. Air pressure and wind are integral components of Earth's atmospheric system, influencing weather patterns, climate, and the distribution of precipitation. These forces drive the movement of air masses and determine the global and local winds that shape our environment. Understanding the mechanisms behind air pressure and wind provides insight into the complex interactions within the atmosphere. Atmospheric pressure, the force exerted by the weight of the air above, is measured using instruments such as barometers. It varies with altitude and temperature, influencing weather systems and the movement of air masses. Wind, defined as the horizontal movement of air, results from differences in air pressure, moving from areas of high pressure to low pressure. The strength of the wind is directly dependent on the magnitude of air pressure differences, or the pressure gradient force, which serves as the primary driver of wind. However, wind patterns are not solely determined by pressure gradients. The Coriolis effect, a phenomenon caused by Earth's rotation, shifts global wind directions. In the northern hemisphere, winds are deflected to the right, while in the southern hemisphere, they are deflected to the left. This effect explains why global wind systems, such as trade winds, westerlies, and polar easterlies, follow curved paths rather than moving in straight lines. The interaction of pressure gradients and the Coriolis effect creates the dynamic wind patterns observed around the globe. Friction also plays a crucial role in shaping wind behavior, particularly near Earth's surface. While winds aloft are primarily influenced by pressure gradients and the Coriolis effect, surface winds encounter friction from terrain, vegetation, and buildings, which slows their speed and alters their direction. This interaction between atmospheric forces and surface features creates the localized wind patterns experienced in different regions. Air masses, large bodies of air with relatively uniform temperature and moisture characteristics, are another essential component of atmospheric dynamics. These air masses are classified based on their source regions, such as maritime tropical MT, continental polar CP, or maritime polar MP. For example, an air mass originating over the warm waters of the Gulf of Mexico is labeled MT, as is maritime, formed over water, and tropical, warm and moist. This type of air mass contributes much of the moisture for precipitation in the central and eastern United States. In Kansas City, Missouri, where weather forecasters monitor regional patterns, the dominant air masses are typically MT and CP. Maritime tropical air masses bring warmth and moisture from the Gulf of Mexico, while continental polar air masses deliver cold, dry conditions from Canada. The interaction between these contrasting air masses often leads to dynamic weather events, including thunderstorms and snowstorms. In winter, MT air masses may even produce nor'easters, powerful storms that affect the northeastern United States with heavy snow, rain, and strong winds. Cyclones and anticyclones are fundamental weather systems driven by air pressure differences. Cyclones, associated with low-pressure centers, involve converging air that rises, cools, and often produces precipitation. These systems are frequently linked to stormy weather. In contrast, anticyclones, centered around high-pressure areas, feature diverging air that descends, leading to clearer skies and more stable conditions. The interplay of these systems shapes regional weather patterns and influences the distribution of precipitation. The global distribution of pressure and wind belts highlights the complexity of Earth's atmospheric circulation. The equatorial low-pressure zone, characterized by rising air and abundant precipitation, contrasts with the subtropical high-pressure zones, where descending air creates drier conditions. These patterns drive the trade winds, which flow from subtropical highs toward the equator, and the westerlies, which dominate the mid-latitudes. Polar regions, with their high-pressure systems, are marked by cold, dry conditions and polar easterlies. In the mid-latitudes, atmospheric circulation becomes even more complex due to the interaction of polar and subtropical air masses. The jet stream, a high-altitude current of fast-moving air, acts as a boundary between these contrasting air masses and influences the development of cyclones and anticyclones. This dynamic system contributes to the variability of weather in mid-latitude regions, including the formation of storms and temperature fluctuations. Local wind systems also play a significant role in shaping regional climates. For instance, sea breezes and land breezes result from the differential heating of land and water. During the day, land heats more quickly than water, causing air to rise over the land and draw cooler air from the sea, creating a sea breeze. At night, the reverse occurs, with the land cooling faster than water, producing a land breeze. Other local winds, such as mountain and valley breezes, are driven by similar temperature contrasts and topographical features. The study of air pressure and wind also extends to large-scale climatic phenomena such as El Niño and La Niña. These events, driven by changes in ocean temperatures and atmospheric circulation in the Pacific Ocean, have far-reaching impacts on global weather patterns. El Niño, characterized by warmer-than-average sea surface temperatures in the equatorial Pacific, often leads to increased rainfall in some regions and droughts in others. Conversely, La Niña, marked by cooler-than-average sea surface temperatures, typically brings opposite effects, with wetter conditions in some areas and dry spells in others. These phenomena demonstrate the interconnectedness of Earth's atmospheric and oceanic systems. Wind and air pressure are also closely linked to precipitation patterns. Global wind belts, such as the trade winds and westerlies, influence the distribution of rainfall by transporting moisture across vast distances. Regions under consistent low-pressure systems, like the equatorial zone, receive abundant precipitation, while areas dominated by high-pressure systems, such as deserts, experience arid conditions. The movement of air masses, the interaction of cyclones and anticyclones, and the influence of global wind systems all contribute to the complex patterns of precipitation observed around the world.